You've just been handed a brief: commercial car park. 10 AC chargers, 2 DC fast chargers, 520 kilowatts of installed EV charging load. One question: how do you connect all of that to the grid safely, legally, and with room to grow? This is the step-by-step engineering design process for an EV charging station, from utility connection to charger terminal. No hand-waving, real calculations, real decisions. Here's our worked example: a commercial car park facility. 10 22 kilowatt AC chargers, Type 2 connectors, 3-phase supply, 250 kilowatt DC fast chargers, CCS2 connectors, direct battery charge. Our job as the design engineer is to size everything between the utility supply and those charger terminals: the transformer, the switchboard, the cables, the protection, the earthing, and the load management system. 3 design objectives: safety first, reliable power delivery, and infrastructure that can scale. Let's establish the fundamentals. There are 3 charger tiers. Level 1, single phase, up to 3.7 kilowatts. Fine for overnight home charging, not for commercial. Level 2, single or 3-phase, 7 to 22 kilowatts AC. This is our AC charger. The vehicle's onboard charger converts AC to DC internally. Power is limited by that onboard charger rating. DC fast charging bypasses the vehicle's onboard charger entirely. The charger rectifies AC to DC and pushes it directly into the battery pack. That's how you get 150 kilowatts. The key implication for our design: DC chargers draw significantly more current from the supply, 3-phase at up to 216 amps per charger for our 150 kilowatt units. Load calculations. Step 1, installed load: 10 AC chargers at 22 kilowatts each, 220 kilowatts, 2 DC fast chargers at 150 kilowatts each, 300 kilowatts, total installed load 520 kilowatts. But we don't design for 520 kilowatts. Not all chargers run at full power simultaneously. We apply demand factors. For a commercial car park, AC chargers, 70% utilization factor, DC fast chargers, 85%, 220 times 0.7, 154 kilowatts, 300 times 0.85, 255 kilowatts. Maximum demand, 409 kilowatts. Now convert to kilovolt amps. Modern EV chargers have active power factor correction. We'll use a power factor of 0.95. 409 divided by 0.95, 430 kilovolt amps. That's our design figure. 430 kVA. 430 kilovolt amps means we need to have a conversation with the utility. Low voltage supplies, most utilities cap these at 3 to 500 kilovolt amps. We're right at that boundary and we want expansion headroom. Medium voltage supplies the right call here. 11 kilovolts. That means the customer installs their own HV/LV substation on site, transformer, HV switchgear, LV switchboard, customer's responsibility, customer's asset, transformer sizing. Next standard sizes are 500 and 630 kilovolt amps, 500 kVA, loading at 430 is 86%, tight, no expansion headroom, 630 kVA, loading at 68%. Comfortable, room for additional chargers in stage 2, we select the 630. Specification: 11 kilovolt primary, 400 volt secondary, DIN 11 vector group, 4% impedance, 50 Kelvin temperature, rise. One important note: utility connection lead times for HV supplies typically run 3 to 12 months. Start the network impact assessment on day 1 of the project. Cable sizing: every cable in the system must satisfy 3 independent criteria, and the most demanding one governs. Current carrying capacity from the AS/NZS 3008 tables, derated for installation method, ambient temperature, and grouping. Voltage drop, AS/NZS 3000 limits. Total drop to 5% from the point of supply to the load. We target 2.5% on the main run, 2.5% on the sub-circuits. Fault loop impedance: the cable impedance must be low enough that fault current is sufficient to operate the upstream protection within the requirement. Results for our system: main LV incomer 430 kilovolt amps at 415 volts equals 600 amps. We specify 2 parallel runs of 300 millimeter squared copper, 3-core plus earth. AC charger feeders, 22 kilowatts, 32 amps, 6mm squared copper, 1 cable per. Protection and safety. The hierarchy runs from utility to charger terminal. At the top, utility HV fuse or circuit breaker, protecting the network. Then HV-LV transformer with primary fuse protection. Then the main LV MCCB at the switchboard, 630 amps, with overload and short circuit protection. Then individual MCCB or MCB protection at each charger feeder. Then the charger's own internal protection. Residual current devices. For AC charger circuits, Type A RCDs, they detect AC and pulsating DC fault currents. For DC fast charger circuits, Type B RCDs are mandatory under IEC 62955. Here's why. DC fast chargers can inject smooth DC fault currents into the supply circuit. Standard Type A RCDs are blind to smooth DC. A Type B device detects AC, pulsating DC, and smooth DC. This is not optional. Earthing and bonding. Our system uses a TNS arrangement, separate neutral and protective earth conductors throughout, from the transformer star point to the charger terminals. Every exposed conductive part, the charger enclosure, the cable tray, the cable management, the vehicle inlets must be bonded to the protective earth conductor. The bonding path must be continuous and low impedance. For DC chargers, the PE conductor sizing follows the standard rule. Minimum 50% of the phase conductor cross-section up to 6. Load management. At this scale, it is not optional. Without a load management system, peak demand can easily exceed transformer capacity, particularly if EV charger usage spikes in the morning or evening peak. Our system implements OCPP 2.0.1, the Open Charge Point Protocol. Each charger communicates real-time power draw to the charge point management system. The CPMS applies our demand limits: 154 kilowatts total for AC chargers, 255 kilowatts for DC. When aggregate demand approaches the cap, the LMS dynamically reallocates power, reducing charge rate on lower priority vehicles and redirecting capacity to vehicles with greater need. The same infrastructure is ready for vehicle to grid when the technology and regulatory framework matures. The CPMS can command chargers to export power, future expansion, design for it now or pay twice later. Stage 1, we're installing now all civil infrastructure, conduit runs, cable trays, and pit systems for the entire planned site. We activate 10 AC chargers and 2 DC fast chargers. Stage 2, additional chargers. Using spare conduit sleeves and spare ways in the switchboard. No new trenching, no transformer upgrade at this stage. Our 630 gives us headroom. Stage 3, if demand grows to warrant it, a second transformer or an upgrade to a higher capacity HV supply. 8-point design checklist. 1. Utility engagement starts on day 1. 2. Calculate maximum demand with realistic diversity factors. 3. Select transformer with expansion headroom. 4. Size cables for the worst case of 3 criteria. 5. Type B RCDs on all DC charger circuits. 6. Install a compliant load management. That is the complete step-by-step EV charging station design, from utility supply to charger terminal, with a real worked example at commercial scale. What would you check first on a new EV charging project? Drop it in the comments. If this walkthrough was useful, subscribe. We publish engineering explainers every week.